Good afternoon to everybody. Welcome to this workshop for presenting a very important initiative that Atos proposed in the domain of quantum computing, or let's say for a training, two training sessions that will be organized by Atos in the next weeks. I think that it will be very important since now to underline that the expression of interest for participating to the two sessions have to be expressed before the next March 19th. All the information will be shared through the EFAB website, and also will be shared and propagated through who has been participating to these sessions of presentations, and as a reminder with respect of what is being come in the next days. I will take very few minutes for introducing a little bit the EFAB Foundation in order to contextualize what it will be these actions from Atos. EFAB is somehow the integrators of the different stakeholders that are dealing with the high performance computing and quantum computing related to the actions for the development process of the Bologna Technopole. The Bologna Technopole, you see hopefully the rendering of the site. It will in somehow host what will be the big data center of CMQF, and also we host the big data center of CNEC and INFN for hosting one of the pre-existing systems procured by the joint undertaking URSPC, and together with many others research labs and national entities that will have a point of presence in that context. I would underline the NATO National Agency, the University, the Biobank and Life Science, the NEA centers, and also, of course, the big data associations and foundations. So that is the overall pictures and the ecosystems where the EFAB it's working. So it's for promoting the strategic national positions in the domain of high performance computing, applied artificial intelligence, and of course their implication, including quantum computing and the quantum technology. The idea is to act as an international influencer and maybe an independent entity that would try to foresee and to support what it will be the development process of the technology and their impact with respect of the, let's say, human behavior and human development. So from this point of view, of course, is to address what it will be the reinforcement of the scientific research, but also to designing a scenario that it would address what are the main scientific challenges, including climate change, health, pandemic, and the exploitations of the resources, and also to support the scientific process with respect of the digital twins of the complex systems, including the digital twins of the Earth systems, and maybe of a different scale, at a different scale, what will be the digital twins of what is the anthropological disseminations at different scale, like urban scale, national scales, and so on and so forth. Of course, the education and training and the outreaching it's a very significant and important actions and missions of the EFAB Foundation, and from this point of view, this present and the actions, it's perfectly in the context of the offers and the objectives of the foundation. Just a few words with respect of the ecosystems, in the sense that the ecosystem is becoming more and more complex. On one side, there is the EFAB, where the founding partners are Associazione Big Data, Unipolsai, and I, and participating Atos. But there are many significant prospects, Leonardo, TIM, FCA, and also some significant participating prospects like other foundations and others potential players, including, just to say Pascal, just to mentioning one of the actors in this specific context, so the context of quantum computing, and of course the members of the big data associations, who is one of the partners of the founders of the EFAB ecosystem. Let me underline a little bit what is the one of the main assets of the foundation, which is the scientific boards. So the scientific board, who is composed by a very renowned scientist at the very high level and at the very international independent level. Just to mention Luciano Floridi, Alberto San Giovanni Vincentelli, Thomas Lippert, Matteo Valero, Florence Rabier, Ursula Baslet, and Anna Grassellino. There are many that maybe are well known from the participants of today. I underline, just to make an example, Anna Grassellino, who is the leaders of the one of the US project in the domain of quantum computing, with a very strong correlation with the national and Italian ecosystem. So that's more or less what are the state of the art. Of course, we are working in some domain in the context of conventional and innovative HPC technology. Quantum computing, it's by definition one of the most exciting and innovative. Then the overall socioeconomic challenge, the climate change and climate services, and life sciences, one of the others main and important topic. More or less, that is what I would like to say. Dissemination and the scientific activities is one of the others very important issues. We are going to address others, let's say, education and trainings actions that will be organized in collaboration with the big data associations and with the national ecosystems, university, academia, and research agencies, with respect of, you see, advanced and innovative topics in the context of quantum computing and the quantum technology. That will be many other occasions. And from this point of view, I would inform and also share the idea that these actions, and so the seed that has been posed by Atos with these let's say founding actions in the domain of education and training for quantum computing would lead to the idea that we would be providing a certain kind of, you see, framework of educations for quantum computing, but also a support action for early adoptions of the quantum computing technology and quantum computing inspired development process, and that it will be in close collaboration with the main partners and the main stakeholders of the context, including others, international organizations, and including others, you see, potential players in such a context. I would stop here from the point of view of this specific topic. I would remind all of you that more information will be propagated with respect of the futures actions and the futures event linked to this specific event related to the expressions of interest for participating to the vertical sessions of training in the next days through the EFAB website. Let me use 1 second for promoting also my second ads, which is one of director of HPC department of CINECA. We have just launched a quantum computing laboratory where the link with Atos and EFAB will be very strong from this point of view, in order to provide access to a service for quantum computing emulators and the simulators, as well the soon availability of the quantum learning computing systems provided by Atos, that it will be make available at CINECA facility in the context of the pre-exascale project, and that of course it will be supported in collaboration with the Atos colleagues at the national and international level. I'm stop here, and I would leave the scene maybe to Adele for saying a few words with respect of the current very last minute actions of the EFAB Foundation, and then to Vincenzo Camarata for the presentation of Atos, and then to Ivano for managing the day-to-day. Thank you very much, and I will leave the scene. Adele, please.
Thank you very much, Sanzio. I don't want to take up some more time, so I leave the floor to Vincenzo Camarata, just to remind you that I'm available for any information, and you can write me. My email address is adele.delbello@ifabfoundation.org. Okay, so it's all on the website. So I leave the floor to Vincenzo Camarata, Atos.
Thank you, Adele. Thank you, Adele. I would avoid to spend too much time to talk about Atos. Today is a very concrete day. We're going to talk about our activities in HPC, in quantum, the quantum initiatives, and in the development of simulators that can be used by the research community to design and to test how the quantum computing works and will work in the future. So, but just to give you in a few words what Atos is, we can say that Atos is a European company. We are under 10,000 people in the world. We work in 73 countries with the size of the business of 12 billion euros. And we are, of course, covers with our competence centers many topics, many domains in the digital technology. One of these domains is related to the technologies for HPC and in the future for quantum computing. And is a division that invests in the technology, are one of the leaders in the world. And the reason why we're working today with you is because we had a good opportunity to install in Italy 2 supercomputers in the supercomputing center in Bologna, One is for the CMWF organization for the forecast weather, and the second one is for the Leonardo supercomputer. Around this, in Bologna, we are developing a community of people that will work in the applications, in the concrete use of HPC in several industries. And we have a cooperation with the University of Bologna around this topic. And today, we want to provide to you what we implement and realize all over the world to develop the awareness about what the quantum computing will do or will help us to do over the next years, starting from the adoption of the programming environments. And this is the scope of the 2 hours today, explain you which is our capacity and what we are going to do with you in the training program for people over the next months. And please, I would say maybe Ivano, you can start to the topic of today. Yeah, we have an agenda quite tight about topics around this. And please, Ivano, thank you.
Thank you very much. I will share my screen. Okay. Okay, you can see it very well. So, hello everyone. My name is Ivano Pullano, and I deal with the quantum computing business in Italy for Atos. Alongside this presentation, there are Xavier Geoffrey and Sabine Caravel who joined me, and they will cover the most technical discussion about the instrumentation of the quantum learning machine and the general features of such a product. I will give you a brief introduction on what do we consider quantum computing, what is the state of the art for the technology, and I will just give a brief introduction on what does Atos QLM mean, because it's something bigger than just a product. So the basics first. When we speak about quantum computing, we refer to something that is pretty different at a very basic level with respect to standard programming, standard computing. And just to lay the basis, we consider the software we use, whether whatever it is on a customer side or an enterprise software, we usually have an interface in front of our eyes. Behind it, we see the code, and while the code is executed, we all see that there are, well, we all know that there are algorithms behind it, and those algorithms are encoded into bits of information, and those bits of information, if replaced into something different, which are the qubits, will necessarily lead to something completely different with respect to what we are used to, just because of the underlying hardware structure that they leverage. So we will have to speak about quantum algorithms that will stay behind something that will, in the end, look very different with respect to what we used to see in our daily life. So what does it mean for us? Well, the reason why such a dramatic change in paradigm is done is pretty obvious, let's say, which is sorry for the diagram in Italian. The reason is that it just go better in some cases. And what does it mean better? Better means that if we take a standard algorithm, which may be any computing operation we are used to see in our daily life, of course, we are used to the fact that the bigger the size of the problem, the higher the load on the computing resources. But in some cases, and in some very important cases, let's say, the burden of on the computing resources grows exponentially with respect to the complexity of the problem, with the size of the problem. So we can be smart. We can use some nice technology to push a bit down this exponential curve, something like moving rightwards on this diagram. But we will never change the shape, because the shape of such a curve is usually due to physical constraints, like having bits and electronic gates on our CPUs and on our binary accelerator. So the promise of quantum computing is that if we change the basis, if we change the physical constraint, we can do things different, and we can change the shape itself of the curve. So we can still expect our burden on the computing resources to increase, but to increase a lot less than what we see on digital computing, on standard computing. And some use cases, some algorithms that are related to such a huge difference are the ones that are showed here. And by chance, it happens that those use cases are, let's say, one of the most important for the scientific community, also because this means, let's say, practical situation that are either highly innovative or highly critical for science and for corporations. So we said, why is it worth it? And let's speak a bit about technology. Technology is right now at a very early stage. It's in its most, let's say, exciting stage, because several ways of doing quantum computing are in development. Of course, some of them are a bit more advanced than others, but in all cases, we all know that technology is still not, let's say, at a sellable state in which we can use it for our daily life. We are still in the experiment. We're still in the labs almost. And moving from the left to the right, just wanted to introduce you what we consider the most promising technologies. We have silicon spin qubits, in which the qubits are not encoded into, let's say, a silicon memory as we are used to, or are not encoded into simple electronic signals, rather than within the spin of electrons that are embedded into a semiconductor device, which means that such states, such quantum states, have the right features, because we know that standard bits don't interact each other, let's say, by design, and they only need gates to work, while such quantum bits require very different interaction. And most importantly, they will need some entanglement, some quantum phenomena that have to happen in order to make them work. And the state of spin of electrons fits very well the case. Second is the superconducting loops, which still exploits the state of spin of electrons, but in a completely different way, because they the system is made in a way in which electrons flow within a loop, and they flow in very particular conditions, which are superconduction. And we can imagine superconduction as a situation, a physical phenomenon in which electrons, let's say, move all together like they were one. And so their state of spin is very easy to predict, very easy to maintain, and it's very similar to having just one of them, with the nice addition of the fact that if there are many, maybe it's better and it's easier to see that, to measure that. So superconducting loops basically work this way, and here you will see some of their features. Just wanted to tell you that the most, let's say, famous QPUs, quantum processing units you will see on the internet are usually based on such an architecture. I will move quickly to ion trap and diamond vacancies, which exploit a completely different way of encoding qubits, and they don't exploit the state of spin of electrons rather than states of energy of electrons, which means that if I, let's say, convince an atom to stay fixed in some position and to not move alongside with its own electrons, those electrons will access only a limited number of energy states. And if such a thing is made in a particular way, that number of states will be just the number I like. And if I like, for instance, 2, I'll say hello to my assistant there. If you just say that you want, let's say, 2 because you have a qubit, so it has to have only 2 values, well, you can do that. And you can do it trapping ion vacancies or ion electrons within a crystal, or putting a dopant element within a certain crystal structure. And that dopant element, again, will have the right energy state number you will like. So let's say this is the second family of quantum computers, and the third family is what we all would like to see, which are the topological qubits, which are just theoretical QPUs that are very nice because in principle they are made in a way in which the surrounding world won't affect them. And this is thought to solve the biggest issue we see, which leads me to this huge dashboard I wanted to show you, which is the fact that right now with the current technologies, quantum bits are not stable enough. So after a while, their value becomes, let's say, unreadable, or their value becomes meaningless. Let's stay on the bottom left of this dashboard, just to, again, speak about technology. We are right now in what is called the NISQ era. So let's say the noisy intermediate era, in which every QPU we build is, let's say, an unstable one. They have to be kept in a very controlled environment, and the information you can gather from them is something that, let's say, deteriorates very quickly. Of course, even if these devices are somehow intermediate, they are very useful to have a real test bed for running quantum computing, for running quantum algorithms. So there's really much that can be done with them. And here on the right, you see the various technologies and the number of qubits that such devices are able to handle. And of course, we expect that as soon as noiseless QPUs will be built, of course, this is pretty much of a long shot for something that we can only forecast. As soon as we are able to build something that is unaffected or almost unaffected by quantum noise and it's modular in a way in which you consider that as a tile that you can repeat as many times as you want in order to have the right computing power you like, well, at that time, those accelerators, those devices will be, let's say, good enough and stable enough to be massively used. So what did we do within such a field? Atos launched almost 5 years ago the quantum program, which is aimed to make quantum computing available to the people in, let's say, what we consider the most reliable way. How did we do that? Well, first we asked the best people we knew to ask for such things. So we put together what we consider the most important, the foremost scientific, the most important scientists in the world of quantum computing, alongside our top managers. Here you see our CEO, our CTO, and two of the most important people in our R&D specifically about quantum. And these people are basically the committee that drives the various fields of the quantum program and tells to the company what's better to do. And after that, actually, what did we do? Well, basically five things. The first is a product which is reliable enough, which is good enough to make the users use quantum computers, write quantum software, write quantum algorithm, test them, and have a feeling of how such code works. So upon this, we made the quantum learning machine. And given the, let's say, novelty of such a field, we decide also to collect a large number of experts that will support these people in discovering quantum computing, in writing quantum code, in testing, and also in finding new application of quantum computing. Third topic is to work to build and to not only to build on our own the next QPUs, which is one thing, but also to give the scientists and the researchers some instruments to make their new QPUs. So we want also to, and I think we managed to do so, we would like the scientists to have a test also for their research about hardware, so they can model, they can emulate, and they can foresee what happens with certain architectures of QPU, maybe even before having them physically, in order to better understand them. Then fourth thing is working on quantum algorithms. Working on quantum algorithms means that we develop science and scientific publication about the performance of some novel algorithms, some new algorithms, and how do they behave in contact with the current state-of-the-art hardware. And last, but just in this list, working on what we consider one of the most important application of quantum computing, which is quantum safe cryptography. And given the fact that quantum computing is a very promising technology in overcoming the current paradigm for cryptography and making information inaccessible from somebody we don't want to access them, this is a very nice tool to break such barriers, but also to build better ones. And we would like to work on how to make people understand the threat, its size and its and also its features, but also how to develop better defenses. Alongside all this stuff, we partner with several customers, with several research institutions, and all these people build what we call the Qlm User Club, in which is a place where to share, basically where to share information, where to share the views, and also where to foster collaboration between the various users, also alongside us, not only just because of us. We would like really our users to work together and to interact. And this is just an instance of what happens between two of our most important customers for the QLM, which are Total and the Oak Ridge National Laboratory, who went out with this collaboration on scientific topics, which also led to scientific publications. So again, this is the feature of the community. The community is driven by the users. We have our leader of the club, which is just, let's say, a facilitator. And for us, it's very important also because we want to interact with this community. We would like to interact with the customer to understand how do they feel in using such a machine and how is their feedback on the program in order to do better every time. Just to be a bit more practical, this is usually this is a nice picture of what happens when the people get together in this club. And basically, the idea is to, again, speak about what the users did, what are their publication, what are their projects when acquiring a QLM, and so making use of it, and to share what in their mind is their best usage. And also for us, as you see at the bottom of the chart, also to brief the community on what's happening next, on what's new on our machine. So what I would like to tell you is just, let's say, an introduction of what quantum means for Atos, and also I just want to tell you that this couple of hours we will spend together speaking about quantum, it's something that is really the first step for us, and it's the first step in by a technological point of view. We all know that we are really at the beginning of a journey, and also it's a first step also for us as a community. This is really something we would like to foster, and this is our biggest occasion to have this in Italy. So yeah, here is also our coverage. Probably you saw something on the internet. By the way, we usually hold our session at the international supercomputing events, so we can expect to be there also in the future, hopefully as soon as allowed and possible, also in person. And so I think that there will be several occasions to catch up and to keep speaking about this topic. Okay, I will just leave you to some short links to what can be done, what has been done recently on our QLM, and this is just, let's say, the tip of a large iceberg. That are several publications based on the QLM, and we hope that that number is gonna increase significantly in the future. So I think that it's Sabine's turn, if I remember well. Sabine, you there?
Yes,
Okay.
I finally managed to join.
Sorry,
so.
Sabine. Sorry if I interrupt you. It's just to remind you that we have also question and answers session. So we have now at the moment a couple of questions from the public. I don't know if you, Ivano, or Xavier, or Sabine are available to reply to these questions.
Sure.
Okay, the first one is what's the difference in using an NVIDIA GPUs in speed and performance compared with a quantum PC?
With a quantum PC means maybe a real QPU.
Quantum accelerator.
Okay, yeah. So, well, it's the difference is pretty significant because those two devices are built to do very different things. When we speak about a super powerful, high performance computing level GPU, we think about a device that is built to strongly parallelize the activity. So to take the things to do, slice them in several small pieces, manage them in parallel, and then collecting the results. While a QPU really doesn't care about that, doesn't care about parallelism. It just works in a way in which you encode your problem, you encode your task in a completely different way, exploiting the properties of quantum mechanics and the quantum interactions of qubits to do a job. And let's say the most important point of contact between these two technologies is that they are accelerators. So they are not meant to work alone. They are meant to do usually part of the job, but the way in which they do the job is completely different, and so the performance will be completely different. We can expect that if I have, let's say, to solve a huge linear system of equation, a GPU will be very good to do so and will be way quicker than a QPU. But if I ask a GPU, let's say, to factorize a number, a very large integer number, well, it will seriously lag behind a QPU. So this is just two examples of how different such machines are.
Okay, thank you very much, Ivano. There is also a further question. In the long term, do you think that the different solutions now adopted to build a QPU will remain, or do you think that one technology will dominate?
Well, I really don't know. I really don't know, because this belongs to the future. I can tell what we are seeing today in the present, which is something like at least for me, it would be very, very nice to see different technologies. It's like having CPUs and standard processing unit, maybe not made out of silicon, maybe not made out of transistors. I think that if things were different with respect to that particular topic, it would be great. We would have a way, let's say, richer environment. So what I can tell is that I really would like to see something like this, but of course we can't tell. We can tell, and we can tell if the current technologies are the right ones. Maybe tomorrow somebody will come out with some nice optical devices made out of glass that will basically just leave the dust on the silicon QPUs and to the ion trap technology. We will never know. So what we are seeing today is something very exciting. Several things work, and it's all to be said which works better.
Thank you, Ivano. There's a further question. What kind of APIs are currently used to interact with the QPU?
Well, this is something that, let's say, at least for the QLM, Xavier will cover very deeply. So I will just introduce a few things. A very important part of our QLM is the software environment. So we all know that we can't just give the programmer, give the software engineer, the QPU, leaving the room and forget about that. Of course, this doesn't make sense at all. So we wrote some Python-based frameworks that will improve the quality of life of the computer scientists. We define that in an easy way and with, let's say, also a multi-level approach in which you can easily program your single qubits and the gates using Python, but you can also optimize your circuit. You can also do some more advanced things, but still within the most standard computing languages, the most standard programming languages. So yeah, we thought about API, we made them, and of course, Xavier will speak very deeply about that in a quarter of an hour or a bit more maybe.
Thank you very much, Ivano. Xavier?
Okay, just let me see one thing. Okay. Maybe if you agree, I will cover a bit more, Xavier, of the presentation. How do you like?
As you want. It seems that Sabine has a few problems of connection, so I can take the following slides if you don't mind.
Please.
So thank you, Ivano. And yes, to make the link with what you have presented with our Atos quantum program, here is a short summary of what we have achieved so far and in which direction we are heading. So as you said, the program has started 5 years ago, and the very first concrete outcome of this program was the Atos QLM. That the first system was sold in 2017. It was installed in Oak Ridge National Lab, and since then we have been introducing new features again and again. So I will be talking a little bit in more details about the noisy simulation that we have introduced in 2018. You have talked already about the Qlm User Club. We will be talking about MyQLM, and but version after version, we provide our customers with brand new features, and they what I would like to insist on is where we are heading. So we are heading with a better integration with the HPC systems, and really we believe that HPC and quantum computing will converge in the near future, and with the use of quantum processor as accelerator to HPC systems. So really have a full workflow where some tasks, where some algorithms, specific algorithm, will be accelerated by quantum computing, thanks to an ISC accelerator that we wish to have in our portfolio by 2023. So on the next slide, maybe, here you have a full overview of our offering. So it's starting on the left with my QLM, which is the programming language, and I will show you some examples of my QLM, and I hope it will help you understand the difference with other programming paradigm. And the MyQLM, what we have done last year was to provide this full programming environment separate from the QLM, and we give it now free of charge. So everybody that wants to start writing quantum circuits can download it for free and start writing their circuit. We provide a lot of tutorials, so you can start with very simple examples and go progressively to quite advanced programming. We provide with that MyQLM also a basic level simulator that will allow to simulate the behavior of a quantum processor, and its scalability is limited, but still already interesting, about 20 qubits. This is really the programming environment. And then if you need a more advanced feature, our main offer and our star product is the Atos quantum learning machine, the Atos QLM. It's based on a large memory system, and it provides advanced simulation like optimization for hardware-specific constraint, noise models. We provide two different ways of simulating quantum computers. The first one, which is based on gate-based programming and circuits, and the other one that is based on quantum annealing. That is a different way to use the quantum properties of the matter inside the quantum processor. And the scalability and the performance for sure of the Atos QLM is much higher than my QLM. We can scale up to 40 qubits, and we can have also GPU acceleration for quantum simulation. And the goal of the Atos quantum learning machine is to be able to prepare code, and I will show you some examples, to all kind of hardware technology. As Ivano said, there is no clear winner today in the race of what technology will be predominant in the future. So this is why this is important to have a programming tool that will be able to adapt the code you are writing to any kind of quantum computing hardware. And on top of that, every system we sell is coming with a full line of service. And on the next slide, you can see an example of the service portfolio we have, our service catalog. So we have service for very beginners, so starting with understanding the stakes of quantum computing, to intermediate service, which is the QLM Fast Start. It's a training, a 2-day training that comes with every system we sell. So that means that when you get one Atos QLM, it comes with this full training, and after this training, you are able to use any of the features of the machine. And growing after that, you can get some consulting services up large proof of concepts, where we identify use cases. We study how these use cases can be tackled by quantum algorithms. We select some quantum algorithm, and we implement this algorithm on our quantum learning machine to assess correctly the benefits of using quantum computing in a specific use case. So there are many ways that you can use the Atos QLM, and the first one was to learn quantum computing. This is why we call it initially quantum learning machine, not to be confused with machine learning, but quantum learning machine. So really the first goal was to get acquainted with quantum computing. But now we see that you can use this machine to develop algorithms, and we have better tools to start writing algorithm and see their behavior, so improving them, debugging them. After that, and this is why now some of us customers are buying our QLM, is as I said, there is no clear evidence of which technology will be the major one in the future. So you have to deal with different ones. And with the Atos QLM, it's easy to optimize your code, your algorithms to run on different hardwares and to compare those different hardwares. And this is why what we have done recently with the announcement of an initiative called Q-Score. Q-Score is based on our tools and it provides a methodology to compare different hardware from a application point of view. And last but not least, the QLM can be used in a hybrid classical and computing domains to run hybrid codes and with a higher and higher convergence and integration with the HPC systems. No, so yeah, just a few words to say that the Atos QLM in fact comes with different models. We have 5 different models, starting with QLM 30 means that you can simulate up to 30 qubit, and it's scaling up to QLM 40 that can simulate up to 40 qubits. And each time you increase the number of qubits by 1, you in fact requires to double the computing and the memory of your simulator. And so it's easy to start with a small simulator, the QLM30, and to upgrade from one model to another anytime you need more power. So I would like to make a quick focus on the latest evolution we have provided with our Atos QLM. The first one is about quantum annealing. Quantum annealing is not exactly a programmable way to use the quantum properties of the matter. It is used by several systems. The most renowned is D-Wave, which is building quantum annealing machines. And with quantum annealing, you cannot program the system in, I would say, the classical way, but you can put your system in a state to be able to solve only one kind of problem, which are the combinatorial optimization problems. But this kind of problems can be found in nearly every domain. You can use, you can map classical problems into a combinatorial optimization problem, like traffic routing, like logistics, supply chain, portfolio optimization in finance. There are many ways, many problems that are of the class of combinatorial optimization problem that can be efficiently tackled by quantum annealing. Second evolution, I will give you a little more details at the end of the presentation. It's about MyQLM that we provide now for free. And third evolution is the QLM E. So the QLM can be now GPU accelerated to provide higher performance in terms of quantum simulation, whether it's noiseless simulation or noisy simulation. I will give you some details, and especially this acceleration is very interesting to accelerate variational algorithms that are hybrid classical and quantum algorithm that are probably amongst the best candidates to take advantage of noisy processor, NISQ processors. So in summary, if I should insist on the most important benefits from the Atos QLM, is first, it's hardware agnostic, so you can prepare code for any kind of hardware, should it be quantum annealing or gate-based programming with superconducting qubits, trapped ion, or Rydberg atoms, cold atoms, or photons, or whatever. It's really scalable, so you can start with a small machine, increase it. It's future-proof, so you are not bound to any technology. In terms of programming, it's based on on standards that are widely used. So the programming language you will see is based on Python. You can use Jupyter Notebooks to have some interactivity. We provide a lot of libraries, a lot of tutorials. In terms of interoperability, we provide as open source modules some interoperability kits that allows you to import and export the code you have done on MyQLM to other frameworks like Qiskit from IBM, or like Google Circ, or Project Q, or Forest from Rigetti. And last but not least, we have a very powerful noisy simulation module that allows to prepare code and to prepare code for real hardware, and understand how your algorithms will behave on real processors. So really, this was the hardware part. I would like in the last part of the presentation insist on the software part and how to program, and what kind of benefits you can have in terms of programming. So I don't know if we want to make a short break to get some questions at this time, or should we?
Yes, Xavier. There is a question. What are the reasons to choose Atos QLM solution instead of a competitor one, such as Qubits kit from IBM?
Yes, Qiskit from IBM is a good simulation tool that can be used on every IBM processors, but only on IBM processors. So if IBM was the only QPU vendor, I said, okay, that's good. You can use their programming environment and to do simulation, to do noise modeling, and to do job submission. What we are proposing here is to do the same kind of programming, optimization, execution of the simulation, submission of jobs, but you can do it by connecting to IBM processor, by connecting to Traption processor, by connecting to other kind of processor, by preparing code for quantum annealing machines. So this is one point. The second point is we have put a lot of emphasis and a lot of effort on the performance of the simulation. And the performance of the simulation, at the end, we are able to simulate larger and much faster circuits than with Qiskit, and we have quite impressive figures on that part. And third is the quality of the noisy simulation. We have a noisy module that is much better than what you can find in other frameworks, so that allows you to run a lot of simulation without the need of running as many simulation on real hardware. So you can spend more time on your simulator and use less time on real hardware. Oops.
Okay, thank you very much, Xavier. So I don't see any more questions at the moment, so maybe we can leave the floor to Sabine.
Oh, I will.
Another question.
Oh, another question. Okay.
Yeah. Is the QLM simulator models extendible by the user? For example, may I add a new kind of QPU or customize the behavior of the provided ones?
Yes, I will show you a little bit all the plugins we are providing to adapt our code to different QPUs, and you will see that for existing QPUs we are providing the libraries already in the QLM, but for the future QPUs we have also a very open interface that allows you to describe new QPUs in terms of topology, in terms of gate set, in terms of noise. So even for QPUs that we don't know at the moment, we are able to import them and to create a hardware model for them. Yes. So I will keep as Sabine cannot, unfortunately cannot connect. She had some network connection issues. I will do the next part.
Okay, thank you. Thanks, Xavier.
So on the software part, I would say that there are three kind of features. One for programming, and you will see that there is an assembly language, but most of the time it's not used. We are using the high-level language, which is called PyAcasm, which is the Python extension for Acasm. So we provide all programming environment in under the form of Python modules. We are providing a lot of libraries also. We are providing methods and classes to solve a combinatorial optimization problem. And as I said, interoperability kits to connect to other frameworks like Circ, Project Q, OpenAcasm, Qiskit, to name a few. After that, we have a full list of optimization plugins, and I will show you some of them to adapt the code to specific hardware. And last part are the simulation part with digital quantum computing simulation. And I will go into detail, and with algorithm to simulate quantum annealing, either in a noiseless way or with the physical noise models. So let's start with a first program. So I'm sorry, Ivano, you will have to click repeatedly. So first, if we want to create a program, it's just we are just using Python, and you can, as always in Python, start by importing your modules. And first, you create a program. You will allocate some qubits, and then you will apply some quantum gates. And when you have done that, you can export your program to a circuit, and you can already display the circuit. So in our case here, I will just make a quick stop. We have a very simple circuit. It's the equivalent of a hello world in the space of quantum programming. We have 2 qubits here, and we have applied 2 different gates, Hadamard gates, that will put my first qubit into a superposed state. So all the qubits at the beginning of my program are in the 0 state. When I apply an Hadamard gate, my qubit 0 will be in a superposed state, so between 0 and 1, or not between, but both 0 and 1 at the same time. And we apply a second gate, which is called the C-NOT gate. A NOT gate, you invert, it's easy to understand, and it's controlled, so this is why we call it C-NOT, control note. We control the negation by the first qubit. And after using that simple circuit, your 2 qubits are in a superposed in an entanglement state. So now, if you want to, so we have written here our first circuit. Now, if I want to execute it, the first thing I have to do is create a job from the circuit. Then I can submit my job to a QPU, and I will explain you a little bit later what I mean by QPU. In that case, it's a linear algebra QPU. And then I can display the results. And displaying the results is just iterating over the state vector. So the state vector is the vector that will, for each possible state, will give you the amplitude of the vector, and the amplitude vector will give you the probability of the state. So in our case, with this very simple program, at the end of the program, I have a two qubit system. When I have 1 qubit, I can have 0 and 1. When I have 2 qubits, I can have 0, 0, 0, 1, 1, 0, 1, 1. So 2 power of n different states. And in my case, I can see that I have, at the end of this program, only 2 states, 0, 0, and 1, 1, with the equivalent probability of 50%. So this is really the most simple example. And as you can see, it has nothing to do with classical computing. So when so a program, basically the equivalent of a program is a circuit, and the equivalent of the instructions are the gates. And you can see here a list of existing gates in our Atos QLM. So there are gates that are providing basic operations like the X gate, which is providing basically a NOT gate, and you have Adamar gates to do a state superposition. But and after that, we have many gates to do all kind of rotation in different on different axes. And we after that we have multiple arity gate, so gates that will be applied to several qubits at the same time. So all the control gates or swap gates or control gates. So these are the basic gate set that is quite universal. So that means that you can write any kind of circuits with that gate set. But sometimes we will see that for some specific hardware, there are some gates, there are existing gates that are not described here. So what we can do with the Atos QLM is very simple. We can create at any time an abstract gate that is just defined by the matrix that will apply to the different states. So like my coupling XX gate here, I have just to describe my gate by its matrix, and it will be available into the QLM. So the other notion you have seen very quickly in the first program is when you have written your circuit, you want to execute your circuit. And what do we mean by executing our circuit? In fact, on the QLM, we have a modular architecture, which is based on a execution stack. So the execution stack, what it is, it's some plugins that are piped one after the other. And at the end of the pipe, you have a QPU. And what I mean by QPU, the quantum processing unit, what I mean by QPU, it can be either a simulator, and I can have different simulator to ideally describe the behavior of a processor, or you can have a noisy simulator that describe the processor taking into account the real-life behavior, and I will explain later what I mean by that. Or this QPU can be a real QPU. So, for example, I was taking the example of IBM processor. You can have access to a real IBM processor. So with the Atos QLM, you can write an execution stack made of plugins, and the last plugin will be an access to the real processor from IBM. And what do we mean by plugins before the QPU? Plugins are used to do some pre-processing and post-processing. And when you have your circuit that is submitted to the stack, the circuit that is committed to the stack will go to one plugin after the other, will be simulated. So during this plugin phase, the circuit may be modified, will be simulated by the QPU and come back from the QPU through all the plugins. And depending on the results of the plugin, can be also loop back into our execution stack. So I was talking about plugins. There are several plugins that are provided into the QLM. If you are using my QLM, you can write even your own plugins. And with my QLM or QLM, you can write your own plugins. We provide all the interface. So by default, we are providing several of them, but you can add also other plugins. So if I, on the next slide, I have an example of one plugin that is used. It's a plugin, the plugins that are used for variational algorithms. So let me explain to you a little bit what is a variational algorithm. Variational algorithm is an algorithm that will iterate between a quantum circuit and a classical optimizer. And the quantum circuit will be used as a problem-specific cost function. So you will encode your problem into Hamiltonian that will be described by a circuit, and you will and this circuit will take into as input will take some parameters, and the goal of a variational algorithm is to find the right inputs that will minimize the cost of the function. And the classical optimizer that is below will be used to decide how to iterate from the values that are coming out of the quantum circuit, to change these values as input parameters, and to iterate up to either decide that you have reached a minimum energy level of your quantum circuit, or that you have reached enough iteration and you will stop. So in the case of maybe you can click, please, Ivano. Yes, in the case of the Atos QLM, we are providing, for example, a SciPy minimizer plugin that can use different methods like gradient descent or optimization by linear algebra. And the quantum circuit will be simulated by the QPU. So you will have an execution stack made of a plugin that is a classical plugin, classical Python program, and a QPU that is a circuit, that is simulating a circuit. And you have many applications of this specific kind of variational algorithms. The first algorithm that is one of the most well-known, the quantum approximate optimization algorithm, QAOA, is made to solve a combinatorial optimization problem. We have also a very famous algorithm like VQE, the variational quantum eigensolver, that is used in quantum chemistry to find the energy level of molecules. We have also research on factoring large semi-prime numbers with variational quantum factoring. In machine learning, we see also a variational quantum classifier. We see for solving linear system, variational quantum linear system, VQLS, that is also heavily studied at the moment. All these algorithms are very interesting because they are not very sensitive to noise and can provide even good results with existing NISQ processors. So we have seen how to write a circuit with gates. We have seen how to run an execution stack with plugins, and this execution stack will use QPUs. And one of the first QPU you will be using is a noiseless simulation QPU. And what you can do with noiseless simulation QPU, you have a different way to use this QPU, and this is where a simulator is behaving, I would say, differently from a real QPU. So the first and the default behavior of the simulation is to obtain the full distribution of the state vector. So that, as I said, if you have n qubits, you will have 2 power of n different states. So when you apply your circuits to all those different states, at the end, you will have a probabilistic distribution of all the possible states with amplitude vector that will give you the probability. And this full distribution, you can have it in a single run. Whereas when you are running on a real QPU, and we can have this behavior in the second mode, the emulation mode, if you run your circuit on a real QPU, at the end you will do measurement, and the measurement will give you only one state among the 2 power of n possible states. And each time you run the same circuit again and again and again and again and again, you will have different results. And most of the time, what you are doing on a real QPU is you are running hundreds and thousands of jobs to get a probabilistic distribution of the result. With a simulator, you don't have to run hundreds or thousands of times. You can have the probability distribution in just one simulation. And we can also, this is the third mode, only compute observables that are only a subtract of what you are interested in, without necessarily simulating the whole set. And it's really useful when dealing with a hybrid variational algorithm. So really, when you are doing simulation, where you compare to real quantum hardware execution, you have a deterministic output, and it's not a statistical result. You have the full state vector distribution. You don't write your algorithm with a hardware constraint in mind. You can emulate all kind of topology, all kind of technology. So when I said a noiseless simulation is using a QPU, in fact, we have in our Atos QLM 5 different QPU that are provided. The first one, and which is the default one, is based on linear algebra, and it can be used for every kind of circuit. But we have other simulators. I'm just mentioning them quite rapidly. MPS that is based on matrix product states, stabilizer using Clifford algebra, Feynman that is using in integral path integral formulation, and BDD that is using binary decision diagram. And for all those 4 different kind of simulator, the linear algebra can be used for every kind of circuit, but the other have some constraints. So if you stick within those constraints, you are able to simulate a larger number of qubits and sometimes faster. So let me take an example. Linear algebra. If you buy a Qlm 30, I said you can simulate circuits up to 30 qubits. That's true with the linear algebra. But if you want to study, let's say, an error correction algorithm that is using only Clifford gates, you will be using stabilizer, the stabilizer simulator that will allow you to go to a much higher number of qubits. So you can, in certain cases, for certain circuits, for specific application, you can take benefit from other simulator to go much higher, to a much higher number of qubits. So even with a Qlm 30, you could simulate hundreds of qubits. Okay, and you can go maybe to the next slide. Yeah, and so this is really the noiseless simulation. But in fact, most of our customers are interested in understanding how programming will behave, I would say, ideally, but they want to understand also how it will fit and how it will behave on real hardware. And when I say real hardware, you have to take into account, we say, 2 different dimensions. The first one is the hardware constraints. So the QPU, the real QPU you have on the market have limited connectivity. All the qubits are not connected all together. So you have to take this into account. And they have also a limited expressivity. So that means that not all the gates are available. Sometimes very simple gates like Hadamard gates on trapped ions are not available. So you have to replace them. So these are the hardware constraints, and I will show you examples after that. And the second thing you have to take into account is the behavior of the noise, which will affect the state of your qubits. So let me show you. Yeah, first of all, the hardware constraint for topology. Here I have just a very simple example of an IBM processor. It's a 5 qubit processor, just like you have as a free access on the IBM cloud. If you look at this processor, you will see the 5 qubits and that are not connected together. In fact, only the qubit at the center, the qubit number 2, is connected to the other. But if you look even more precisely, you will see that the connectivity has also a direction. So that means that you can control from the qubit 2, you can control qubit 4, qubit 0, and qubit 1, but you cannot control qubit 3. So when you are writing a circuit, so I have an example on the top, which is a very simple circuit for doing a quantum Fourier transform on 5 qubits. You will see there are Hadamard gates, control phase gates. So the Hadamard gates, there is no problem because it's a single qubit gate. So we don't have any topology issue. But for the control phase gate, they are using 2 different qubits. And those 2 different qubits, for example, for the first control phase I have on my slide, that's okay. The second is okay, but the third one, you cannot control qubit 0 from qubit 3. So what we have to do is to insert some swap gates that are made of Hadamard and CNOT gates just to be able to replace this simple circuit in something much more complex. And we have done the exercise here. We had for this 5 qubit QFT 15 gates, and if I want to take into account the exact behavior, the same exact behavior on a quantum circuit, but that is compatible with my topology, you will see that it will end up with 85 gates. So we have multiplied the number of gates by a factor of 6, nearly 6, just to take into account the topology. And this exercise, you can do it by hand for very small circuits, but for large circuits, it's impossible. So this is why we are providing a plugin that does it for you. Second example of plugins, it's about the gate set. As you have seen on the previous circuit, for the QFT, we are using a lot of control phased gates. But on superconducting qubits architecture like IBM or Google or IQM, we do not have the control phase implemented by default. So we have to replace the control gate by the control phase gate by a sequence of gates that are made of shift phasing gates and controlled node C-node gates. But if you look at trapped ions, like Honeywell or AQT or IonQ, this exactly same gate cannot just be transformed into the same sequence. It has to be transformed in another sequence of gates that are available on this topology. So when you are writing a circuit, you are just focusing on writing your circuit with control phase gate, and after that, the topology coming from the plugin, the pattern manager plugin, will transform you your circuit to a circuit that is compatible with the gate set. And as I said, you have to take into account hardware constraint, and you have to take into account the noise model. So what do we mean by noise model? You have your ideal circuit, and if you look at the hardware model, your circuit will be affected by all kind of noises that can be coming from very different sources, and it will end up with a circuit that is noisy circuit, and we take into account the noise of idle qubits. So what is happening when you your qubits are not used, and you will have some irreversible changes, and you will have also to take into account the noise when you are passing through the gates. So really, we have a model that will take into account all these kind of things. So yeah. So what kind of tools do we need for a noisy simulation? So the first one, you can please click. Is okay, you start with your circuit, and the good news is the circuit that will be using for noisy simulation is exactly the same that for noiseless simulation. But so we start by doing a noiseless simulation first, and after that we are applying the hardware constraints that are coming through Python's modules. So what kind of constraints we are taking into account? The first one is the gate spec. On the next slide, please. The gate specs is related to the gate. What kind of, for example, what is the duration time of passing a gate? The duration of passing a Hadamard gate is not the same as passing a CNOT gate. On superconducting qubits, it's much longer to go through CNOTs than through Hadamard gates. So this is the first. And the second is the environment. What kind of noise? So we have noise when the qubits are idle, and we have noise when the qubit go through gates. And to explain you how we can model noise on the next slide, I would say there are in the Atos Qlm, I would say two different methods. The first one is based on a classical model of decoherence that is using two processes, T1 and T2 process. So the first process, the T1, is amplitude damping. So that means that when a qubit is in idle state, it tends to come back to the lower energy state. So you have some kind of relaxation that is coming over time. And the second phenomenon that is appearing also is a decurrence time based on dephasing. So when your qubit is idle, you will lose the phase. And those two processes are based on two time variables, T1 and T2, that will give you a rather good model of what's happening. But this is a really basic model that will apply to all the qubits, and that will apply exactly the same to all qubits, whatever it is. In real life, it's even more complicated. So this basic model can be used by simply gathering standard information that is provided by the QPU vendors. The second way to have an even better understanding of what's happening is using quantum state tomography. So a quantum state can be fully described by its density matrix, and what we are doing while using tomography is we are preparing a lot of input states, and we are doing a lot of measurement. And so we can, even if we don't have a model of the quantum state, we are deducing this model from the measured data. And this is really useful to get a good benchmarking or a good verification of a quantum devices. Okay, so to get back to something probably more practical, as I said, we are providing today MyQLM. So what you have seen are example of programs, and especially the first one can be used on MyQLM. For the advanced features like noisy simulation, this is not part of MyQLM. This is part only of the appliance that is the Atos QLM. But still, with MyQLM, you can use it whether you are a data scientist, a developer, a tech enthusiast, a student, or a teacher. You can benefit from the many tutorials we are providing. So just to explain you the difference we have between MyQLM and QLM on the next slide. Remember on the QLM, you have what is on the left, the programming stack is exactly the same, but we do not provide any quantum annealing programming methods, but we are providing the same language, PyACASM, with the same libraries, the same interoperability kits. In terms of optimization, we do not provide any optimization tool, which are based on plugins, but we provide a way to create your own plugin. So if you want to create an optimization tool by yourself, you have all that is needed to do so. And in terms of simulation, we do not provide a noisy simulation. And in terms of noiseless simulation, we provide a basic noiseless simulator. And you can write your own simulator because it's also an open architecture. And we provide the noiseless simulator as an open source module, so you can write your own simulator if you want. So in terms of resources, what you can find on the web, on the next slide, please, is if you start with the atos.net/myqlm, you will find all these resources. You will find the documentation on GitHub. There is also a bug tracker. You have all the open source modules that I've mentioned on GitHub. We are providing a lot of tutorials that can be downloaded also from GitHub, or you can run them directly on MyBinder. This is a Jupyter as a service in the cloud. You have a community forum on Slack. We are publishing on a regular basis articles on Medium. So you have a full ecosystem to help you starting programming with MyQLM. So as a conclusion, I would say that quantum computing can be used to solve many kind of problems, combinatorial optimization being one of them, but all kind of problem in different industries. You can get acquainted with quantum computing thanks to tools like MyQLM, and even it requires time. We think it's the right time now to invest time, energy, effort, money into getting acquainted with quantum computing, because changing mindset in terms of programming requires time, but we provide tools to do it.
Thank you very much, Xavier. There is a question from someone is asking from the public if there is a way to estimate from the simulation of the expected speed up of the quantum algorithm in respect to classical solution of the same problem.
This is a hard question because yes, with the simulator you will have a better understanding on the algorithm, how it behaves, and you can estimate the complexity of the algorithm. And from that complexity, you can see what kind of speed up when you have to deal with a specific size of problem. The difficulty most of the time is to estimate correctly the order of complexity of an algorithm. You may find on I don't remember the exact website, but if you look on Google, it will give you it's a quantum zoo website where you can find I think something like 200 different algorithms, quantum algorithms that are existing and that have been assessed in terms of quantum speedup thanks to the evaluation of the complexity. So this is one part. But having said that, I would say for variational algorithm, the proof is even harder to find, and this is where quantum simulation can be very handy, because the theoretical acceleration of a quantum algorithm is not always easy to assess. Sometimes we don't even very well understand how it works. So in terms of speed up.
Okay, thank you very much. There are some further questions about the way in which Atos is collaborating with the University of Bologna.
Maybe I can let Ivano answer this one.
Yeah, definitely. Well, the idea is this. We would like at this stage, of course, to engage with IFAB, which means that we would like really to have a sort of collector of users' experience of needs that come from the different stakeholders at IFAB, and in a way in which we can deliver on our side our let's say knowledge and resource transfer. So those things will be made available to the IFAB in a way in which also all the stakeholders can access them. And we really would like also together with IFAB to build a community of quantum users there in order to have what we discussed about the Quantum User Club, in a way to, you see, have you speak up about what's happening on your experience on the QLM and how does it work, and what you think could be useful for. So at this stage, I would like to say that the collaboration is made this way. Of course, things may change, things may be discussed, but right now everything passes through IFAB when we speak in general about the Bologna ecosystem, let's say.
Thank you very much, Ivano. I perfectly agree. And if you need some more information about our project, I'm available. You can call me, you can write me. I can provide you with all the details. The project you find on the website is something different with respect to the collaboration we have with Atos. So if you need more details on this project, please feel free to write me and I will provide you more information. So I think we are perfectly on time. So thank you very much, Ivano. Thank you very much, Xavier. I'm a bit sorry for Sabine. Maybe she has some troubles with the connection.
Yes, she's sorry. She texted me some messages and
okay.
saying how sorry she was.
Okay, thank you so much. So maybe we can take some more questions. Is there any questions from the public? Not at the moment. Okay. So maybe in the meantime, I can remind you some important information. First of all, the deadline to express your interest is March 19. We can accept up to 12 people. And for this reason, we kindly ask you to send us a resume and also to motivate your interest to the training course. This training course will be held at the end of March and will last 4 half days from 9 a.m. to 1 p.m. On the 29th, on the 30th and 31st, and on the 1st of April. It will be held in English, and there will be a theoretical introduction on quantum programming, but also a practical part, a sort of immersion in the quantum learning machine, in the software environment, of course. And the course will include also the possibility to access the machine for a trial period after the training. Correct me, please, if I'm wrong, Ivano and Xavier. The course in this phase is an experimental course, training course, and will be offered free of charge. And so this is a pilot course, and that's exactly why we expect strong interaction with participants. So I don't know if you would like to add something more, Ivano, Xavier, on this.
Well, actually, not at this stage. I think you covered all of the topics. I don't know if there are some extra questions that came from the audience. Okay. So I don't know.
Okay, yes. One of these is if we are planning to organize more tutorial sessions.
Well, if I can answer, the answer is that is exactly what Adele just mentioned. The following courses will be way more detailed about this and will be really much oriented towards writing stuff and running stuff on the QLM. So for the people who will choose to go for the fast start training, there will be plenty of tutorials.
Okay, thank you. And they would like to know how they can register. So we will publish on the website all the instructions, the deadlines, and all the instructions to register, or better, to express your interest in this phase. Okay, so then we will select 12 people to be accepted for the this first experimental course, and then we will send you all the information and instruction. Okay. Okay. There's a further question. Combinatorial problems seems to be the most interesting one to be approached with quantum machines. In the field of machine learning, hyperparameter optimization is a big problem, and it is combinatorial generally. Do you think that this kind of problem could be interesting to be addressed with quantum machines?
Oh yes, definitely. Combinatorial optimization problem is a very important class of problems, and that can be addressed either by quantum annealers, but that are not really programmable, I would say, and by gate-based programming. I've mentioned one of the algorithm, which is a QAOA, which is really targeted at proposing some implementation to solve combinatorial optimization problem. And one very important application of this is really what you mentioned here, the hyperparameter optimization for deep neural networks, and where this is basically an optimization of parameters with large number of parameters, large number of variables. And there is a very huge activity research at the moment on what we call quantum machine learning, which is exactly what is about is how to use quantum algorithm to accelerate machine learning, and specifically the training phase of a model. So if you have a very deep network with a lot of parameters, using a quantum algorithm is a way to accelerate this training. And after that, you can infer the model with classical computing. You don't have to have a quantum processor to take advantage of a trained model. But to train the model, you can expect much higher performance and a very reduced time, and probably, and why not thinking of doing it in real time. So yes, it's a very active research topic, yes.
Thank you, Xavier. Any more questions? Okay, it seems not at the moment, at least. Okay. There's a further one. In a completely hypothetical scenario, what could be the optimal ratio between CPU and QoPU in a cluster?
At the moment, there is really this answer cannot be, this question cannot be answered at the moment like this. What we see, as we said, is using QPUs as accelerators, but the acceleration that is provided by QPU is very problem specific. So sometimes some algorithm will provide a linear acceleration, sometimes exponential acceleration, sometimes just quadratic acceleration. And really, we can expect, we cannot expect to have a fixed ratio of what seems good to. So, and at first, as progress are being made, at first I will expect to have only a very limited number of QPUs, but we know that things may change heavily in the coming years. So there is no simple answer to the question, and it's because it's really problem specific, problem dependent.
And maybe if I can add a small piece to what Xavier just said, in general, it's very hard to define the ratio between the, let's say, general purpose computing units and the accelerators, whatever they are. So we, me and Xavier and the rest of our teammates basically work also on high performance computing architectures, in which I can tell you there's absolutely no fixed ratio between, for instance, the CPUs and the GPUs. We can see some standard ratio within one machine, but nothing can be told for an entire cluster. So yeah, this is really something that goes down to how you are foreseeing, how are you planning to use the computing resources to do what?
Thank you, Xavier. Thank you, Ivano. Any more questions? Okay. So if there are no questions at the moment, maybe we can close. And I would like just to thank you, all the rapporteurs, Ivano, Xavier, also Sabina, and thank you very much to all of you for your participation. So you can send your interest to my address, my personal address, adele.delbello@ifabfoundation.org. Okay, but you will find information on the website of the foundation, www.ifabfoundation.org. Okay, so we will publish every information on the website. So maybe Vincenzo, would you like to add something? Vincenzo, are you here? No, maybe.
No, I'm here. No, I would say thank you to all of you for the attention, the time spent with us today. And we expect a lot about this cooperation with IFAB. And we're really, enthusiastic to work with you and to have a lot of people that will follow our causes and to generate ideas. Because the basic reason why we are here is to establish a relationship, a collaboration, a partnership that can generate here in Italy, potentially in Bologna, a team of people that can use the new wave of technologies that we are working on. So thank you very much for your time.
Thank you so much, Vincenzo. We hope to collaborate with you too. Thank you so much to all of you once again, and we'll keep in touch.
Thank you. Bye-bye.
Bye-bye.
Bye-bye. Bye-bye.
Thank you. Bye.